For our next video of today, we'll look at active ranging. So if a robot knows where it is at and it has a map of the environment, then in principle it knows where all the objects are in that environment. However, first point is it doesn't always exactly know where it is at, and more importantly, environments tend to be dynamic, so things in the environment change. So even if you have a map of the environment, then there's potential that some of the objects have moved in that environment, and we have some objects that are naturally moving around, for example, other robots and people. So what we need on the robot is sensors to be able to detect these objects. So as a first sensor, we usually have some kind of tactile sensor on the robot, and this is a fail-safe. So if all of the sensors fail on the robot, we know that if the robot has collided with something or touched something, then it's very close proximity and it needs to stop. So this is our fail-safe sensor or tactile sensor. We will come on to pressure sensing and force sensing a little bit later, but for now we'll just look at trying to avoid obstacles. So there's two classes of these tactile sensors. You can either have a robust one. So in this case, we've got a nice sturdy bumper on the robot. If something hits that, it's going to compress the spring. It's going to close this contact here, so close the circuit, so you know the robot's collided with something, and therefore it should stop. Good thing about this sensor, or this bumper, is it'll protect the robot. So it'll stop the robot getting damaged from hitting something. If you want something a bit more subtle, so for example, if it runs into a person, you don't particularly want to damage the person, you can have more mechanically compliant sensors. So for example, this whisker sensor here. So it still knows if the robot touches something because this whisker will flex. It'll close the contact with this loop here and then close the switch. And again, so you know the robot needs to stop because it's in close proximity to something. For the whisker case, it doesn't damage the environment, but it doesn't protect the robot at all, unless it can stop in time. The bumper will mechanically or physically stop damage to the robot. So this is our fail-safe sensor. We don't really, or hopefully we won't need to use this at all if the other sensors are functioning correctly. It is just a backup option. So in terms of our main sensors used in our robot, we'll typically use infrared and ultrasonic sensors. In terms of infrared sensors, there's two types. So they pretty much all look like this. But for this scenario, what happens is the sensor sends out an infrared beam of light. That beam of light gets reflected back, and the sensor measures the intensity of that reflection. Because the intensity will be an inverse square law function, so if you double the distance, you only get a quarter of the light coming back. Then this plot here, you can use to then calibrate the distance. So as objects get further away, the light level falls off on return. The reflection is fairly consistent for different materials, but not for all materials. So for example, if you're trying to measure something transparent, for example a glass window or glass door, you might not get any reflection back, and therefore you won't be measuring that object. The other type of infrared sensors use a position sensitive detector, and what these do is send out a beam of light. So they send out that, and then this light gets scattered in all directions, but some will go back to the sensor, and then this gets focused onto a position sensitive detector. If you know the position that the light's hitting this sensor, then you can use some basic trigonometry to work out the distance the object is. So as I said, our other type of sensors typically used is an ultrasonic. An ultrasonic comes into the category of time of flight measurements. And what these do is send out some energy into the environment and then measure the time it takes for that energy to come back. There's typically two types, sonar and LiDAR. So sonar uses sound waves, LiDAR uses light waves to do the measurements. And there's three differences by doing it via sound rather than doing it by light. First thing is sound requires a medium. Light will travel through a vacuum. So not much difference if you're on Earth, but if you, for example, you go to the moon, an ultrasonic sensor will not work on the moon because there's no atmosphere there to transmit the sound. The second difference is the speed. So the speed of light is 3 times 10 to the 8 meters per second. The speed of sound is 330 meters per second. Because this is relatively slow, the speed of sound, we can use just straightforward a timing measurement to measure how long it takes for the reflection to come back. Because the light is so fast, then we have to use a slightly different technique in order to do that timing measurement. The most important difference is the wavelength. So the wavelength of sound, you're looking around a centimeter for an ultrasonic sensor. The wavelength of light is talking about hundreds of nanometers. Now the reason this is important is because of reflection. So if I just go on to paint. So if you have a surface, so we'll put that. So this is our reflecting surface here. If the wavelength of the light, or if the wavelength of the energy coming in, so there's our waves of energy coming in. If this wavelength is larger than any roughness on this surface, then what you do is you get a mirror-like reflection and the waves bounce off, so it's hitting the mirror. If, on the other hand, do a different colour. If you've got this roughness here, the waves coming in, the wavelength is coming in is smaller than the roughness. When this hits the surface, what you'll do is these waves will be scattered in all directions. Okay, so long wavelengths, and how the energy scatters depends on the wavelength of the energy coming in and the amount of roughness on the surface. If the roughness is less than the wavelength coming in, you get a mirror-like reflection from the surface. Okay, so you get a specular reflection or mirror-like reflection, typically for ultrasonic waves because you've got long wavelength, and you get a diffuse reflection, typically for your LiDAR for light sensors because of the short wavelength. So this has implications when we're taking the measurement. So if we look at the ultrasonic sensor first, this is typically how an ultrasonic sensor works. You have a membrane, so this is your membrane here. So it's just like a flexible plate. And what happens is you apply a voltage across here, so put a high voltage on this plate here. This makes this mechanically move, so it vibrates and sends out a sound wave. Just get rid of that. So it sends out a sound wave. Try that again. This sound wave bounces off your object, comes back, and as it comes back, it moves this plate, and then this motion again can be detected through some kind of capacitive sensing. So that's the basic principle of how an ultrasonic sensor works. You send it out at frequencies higher than hearing, so you don't have all this sound coming from these sensors. It's beyond our hearing range, so they appear silent to us, but the frequency is typically 50 to 60 kilohertz. And the beam profile, you've got a certain width to this, so this is typically a few tens of degrees. So it could be anywhere from 15 degrees up to 30, 40 degrees beam width. Because objects, or the material the objects are made of, absorb certain frequencies, then the ultrasonic sensors send out a range of frequencies. And some of them will get echoed back, and the first one that gets echoed back, it's the time of that first echo gets measured, and that's how the range is determined. There's various ultrasonic sensors available. The Polaroid used to be the most common one, and they're very good sensors. They tend to be less fashionable these days because they took a little bit more electronics to operate them. They're quite high voltage operation. This type, Daventech and versions of it, this uses a separate transmitter, so it transmits and then receives on a second membrane. But you can get single transmission receive ones, such as the Maxona. Now, when I discussed reflections, so it's a mirror-like reflection from ultrasonic sensors, this is where the problem comes in for ultrasonics. So a typical ultrasonic measurement would be this scenario. So you've got your ultrasonic sensor here. You send a beam of sound waves to the wall. So you send a beam up in this direction. So you send a beam up here in this direction, it gets bounced off the wall, comes back and measured by the ultrasonic sensor. So that distance measurement is accurate, that's fine. Because you've got a certain beam width, then it's very hard to resolve the size of objects. So in this scenario, the bottom scenario here, so in this scenario, we've got a small object in front of the wall. The ultrasonic sensor will get its first echo from this small object here. So it cannot see the size of the object, it knows it's close. So they're good at measuring distance, but not so much spatial resolution. If you approach a wall from an angle, then because you're getting this mirror-like reflection, the energy is coming in and bouncing off at this way. And if you see this path here, so this path from the extreme of the beam angle, it actually comes back to the sensor quicker than you'd expect. You'd expect a measurement to come back from this part of the wall, because this is where you're looking and this is what you think the distance measurement is going to be, where actually the distance measurement is coming from this part of the sensor. So the measurement is underestimated. You think it's actually a shorter measurement than it actually is. If that angle gets too extreme, you get this case, and although there's a wall there, the ultrasonic sensor doesn't see it because all the energy is bounced away from the sensor and none of it returns. You can get a scenario if you approach something, for example, like a corner of a room, where again, all the energy is bounced away from the sensor, none of it bounces back, so again, you wouldn't see an object like this. In practice, this doesn't usually happen because what you have is a slightly rounded corner. You never get a perfectly sharp edge to things. You usually get a bit of a rounded edge. And it's on this rounded edge here, you'd actually get some reflection. So it's unlikely for this scenario to happen, but it is possible. On corners, you tend to get multiple reflections. So if you see this scenario here, the robot or the ultrasonic sensor is pointed at this point of the wall here. But the way the beams are bouncing around, the first beam to come back translates this path here. And this distance is actually longer than what this actual line of sight measurement is. So in terms of corners, ultrasonic sensors tend to overestimate the distance to a corner. So it's just something you've got to be aware of. Ultrasonic sensors do give good measurements, but there are errors associated with them and you have to be careful when interpreting the results. LiDAR are similar to ultrasonic, they're sending out energy, but this is a beam of light it sends out. And then measures the reflection, or measures the time of flight of this. Now it's very hard, because light travels so fast, then it's virtually instantaneous, the signal coming back. So it's quite hard to do a time of flight measurement. So there's a trick with LiDAR, and what they do, so if I just go back to Paint, is they send out a beam of light so this is the intensity of the light, but rather than send out light of constant intensity, they vary the intensity of the light, so they modulate the intensity. Okay, so the wavelength of this light, if it's say a red laser being used, then the wavelength is something like 630 nanometers. So that's the wavelength of the light. However, you can have a modulation wavelength, and this is essentially your modulation wavelength. So we'll call it lambda m, and this is how quickly you are switching changing the intensity of the light coming and going. So the point of doing this is the light beam you send out, and in your sensor what you would have is, so there's your sensor, you're sending this beam of light out, it's getting reflected back, and then that will then be directed to a sensor where this beam is also directed that way. So what you're doing is you're comparing this outgoing beam with the returned beam, and the returned beam might look something like that. So what you're doing is measuring the phase shift. So you're measuring this change in phase of the intensity variation of the light that is returned compared to what you sent it out as. And this phase shift gives you a measure of the distance. So what you can do is, depending on how quickly you modulate this light, so for example, if you modulate it at a speed of 15 megahertz, so you're varying this light sort of bright, dim, at a speed of 50 million times per second, then that corresponds to your modulation wavelength here. So this modulation wavelength, in that case that would be 20 meters. Because it's a round trip, that corresponds to a range of 10 meters. Okay, so by modulating at this frequency, you can range up to 10 meters, assuming you can measure enough of the reflection of the light coming back at that distance. Typically, I've said if you can measure within 1 degree, so in this case, if you measure 1 degree of phase shift, you can measure 6 centimeters of distance, or to an accuracy of 6 centimeters of distance. In reality, these LiDARs will measure about 1 millimeter accuracy to an object. So you're looking at phase shifts of sub-degree in order to detect. The range is limited by this modulation frequency here, because although you can measure phase shifts further than that, you only really want to measure a phase shift up to this point. If this wave gets so long detected that you actually go beyond 360 degrees, you don't know if you're measuring a phase shift of that amount or you're measuring a phase shift of that amount. Okay, so this wavelength, you're assuming it's going to be just within 1 wavelength of phase shift, and therefore that limits the range. So this is a typical LiDAR sensor. So we've got a few of these in the school. So this is a Hakoyu. They're quite expensive. So this one's about £2,000. So compared to your ultrasonics and infrared, which are about £10, these are very expensive sensors. They are very accurate. So they will measure distance very, very accurately, but they must be scanned. So it's only a point measurement. So in order to get a 2D or 3D view of the place, you have to move this point of light around. So there's a scanning mechanism in this. This is a 2D scanner. So this will send a beam of light out, measure it in that direction, and then scan the laser to different points and do measurements across a certain angular displacement. Okay, so it's a scanning system, does the measurements within a millimeter accuracy. It won't measure, it needs reflection coming back of objects to do the measurement. So things like transparent objects, glass doors, windows, etc., it'll just see straight through, so it won't appear that there's anything there. So this is why you need a range of sensors on your robot. An ultrasonic would see the glass door but wouldn't be a very good measurement. A LiDAR would give you measurements of all the other objects but wouldn't see the glass door, for example. So by using different sensors, you can compensate for all scenarios. The last one I'll just briefly mention, so these are recently out, is radar systems. So I tend to think of radar as sort of big dishes trying to spot planes flying over. You have got short range radar now, so it's a lot smaller scale. Does ranges, rather than talking about trying to measure planes in the air distance of kilometers, these short range are accurate to millimeter accuracy within tens of meters of range, and everything comes as on a board. So you've got all your signal processing and that, you've got your antenna, so this is your antenna part here, so this sends out the radar signal and measures the return signal. So very, very clever sensors. So I won't go into the details. As I said, these are quite new, these out, but I've given you a couple of references there to look at. First one is how they work, and then the second one is showing you an application of a robot using it to sort of scan the environment and detect where objects are. So it's similar in principle to, for example, a LiDAR, where you're scanning the environment and looking around for objects, but very nice piece of technology, longer range, and commonly used, or getting used more and more in things like autonomous cars, where you need that extra range capability to detect where objects are. So I recommend having a look at them two papers, them two web pages, to find out a little bit more about them sensors. So that concludes our sort of object detection type of sensors. So in our third video of today, we will look at vision sensors, so looking at cameras, etc. And then given an image, how do we go about processing that image?